So today we're going to start tying everything together and look at loop shaping the way I'm going to teach you. There's a bunch of different ways. But the inner SAS loop becomes crucial when you have an unstable system. It becomes crucial because you got to get these poles back into the left-hand plane before you do loop shaping. And we're not going to deal with the really hard one if I have a right-half plane 0 that's going to suck up that pole. That makes it really difficult. You might have to call Gunter Stein at Honeywell and hire him to fix those problems. Or use something like the modern control to get started. So you can see why if I was doing loop shaping in a SAS on this F-16, F-18, any modern fighter that's unstable, you're going to have this type of situation. And the control engineers in the late 70s and early, they prided themselves on being able to stabilize these systems with electronics, fiber-wire. So they wanted to put this pole farther and farther out. Because the farther and farther out you put that unstable pole, the more maneuverable the aircraft comes. It wants to go where you want it to go, like right now. And the F-16 is so maneuverable that I was telling the students last night in the extra office hours, it's so maneuverable that it will black the pilot out, right, before he's aware that he's under a G-load. That's a very bad thing to do. Because if you know you're coming under G-load, then you can get your body ready for it. You can tighten up your muscles, you can force your blood, keep your blood up in your head area, up to 6, 7, 8 Gs. 9 Gs for some young men. But if your aircraft is too maneuverable, and you pull the stick back without warning someone, then you haven't done anything, and your blood instantly goes down away from your brain right away, and you black out with no notice. Right? And this happens to many F-16 pilots. Lost a few airplanes that way. Because when you wake up, it isn't like waking up from a tunnel vision. Your tunnel vision goes out in the G's, and then it comes back like that. But when you black out under a highly maneuverable blackout, it's like waking up in the morning. You wake up like you're in bed. Oh, you see the ground rushing up at you, and then you realize it's not a dream. You're actually in that airplane. So bandwidth now, for unstable systems, when we control them, bandwidth becomes the enemy of stability. The higher the bandwidth, the more problems you're inviting for lots of reasons. That's what we're going to pretty much cover today. If I want to do SAS feedback on this, if I got Mike here, Mike, I want to do SAS feedback, I'm going to put a gyro on this, I'm going to feedback rate, right? The feedback rate, it'll go through an S. So what am I going to put on this diagram if I feedback a rate with an S? That's going to put a 0 here, yes? Yeah. Right? Now do you see the problem? If you know the root locus rules, you see the problem right away, don't you? The roots are going to go from the pole to the 0. I will never get a stable airplane. So I give you a hint in last year's final. I say build an actuator, and we're going to pretend, we don't have to pretend, but we're going to say that your actuator has a programmable 0. So you have a programmable 0, and your actuator is out here, wherever you want to put it, and has a programmable 0, and you can program the 0 from 0 to -5. You can program it. That's part of the problem. Okay? And that will help you now, because now you can see what's going to happen at the low frequency end. These roots are going to come together. This is probably going to go to the 0 this way. And with luck, the roots will come up, and they'll come up like this. Yeah, with luck. With luck. But since it's my inner SAS loop, I'm looking for a bandwidth on my inner SAS loop. Probably what's going to happen is these guys are going to come together like this, and they'll go almost straight up. And I'm not sure what they'll do over here, but you're going to be close to the J omega axis, so you're going to be careful where you're going to pick that inner loop for your bandwidth. The bandwidth requirement, I think, is 10 radians per second. We want to make it only as maneuverable as it needs to be, right? Because the unstable situation, this pole always exists there to bite us. Okay. So let me give you an example of one way that pole will bite you. This is the second or third example in that video by Gunter Stein. It talks about a Gripen, Swedish Gripen. And like I said, every airplane the Swedes make, same thing happens. Guy's on final approach, right? Gets into a pilot-induced oscillation, what we call a PIO. Gets in his PIO, bails out right before it crashes. And then they go to Calspan Corporation in Buffalo and say, what happened? And they always say the same thing. Well, the pilot got out of phase with the aircraft and was pumping the stick too hard. He depleted the hydraulic system. Once the hydraulic system is depleted, the control surfaces, they're still moving, but they're exactly out of phase with the motion that you've got, right? And then boom. So they blame the pilot, like everybody does. They blame the pilot. It's really the design. It's the design of the control system. The airplane did not need to be that unstable, one. And the second thing is, those controls in the cockpit are rate limited. In other words, when you move the stick as fast as you can, the elevator seems to follow your stick, but it's actually rate limited because it doesn't want to break the hinges back there. There's hinge torques that are limiting. So there's some kind of integrator in there that's limiting how your signal gets back. Well, that rate limiting for an unstable system can be too slow to control the system. See what I'm saying? The rate limiting that's inherent in a control system may be too slow to control an unstable pole if it's out there too far. And you will lose the airplane. It isn't, I missed that approach. It's, you'll crash. Best example of that is the Chernobyl example in that video. If you have time to watch that Chernobyl example, it was a man-made disaster. They disconnected all the control loops because they wanted to play with the nuclear reactor. And they played with it and got into this unstable area. You have to go through an unstable area when you fire up and when you fire down a nuclear plant. It goes through an unstable situation. It's all tightly controlled. They disconnected all the controls, and they put the Chernobyl nuclear reactor right in the unstable condition. When they finally recognized what had happened, they, just like the aircraft, the steam reaction took off, and the control rods, they reconnected the control system, but the control rods couldn't go in fast enough. They were rate limited, and the instability blew a 1,000-ton dome off the Chernobyl, killed them all, killed everybody in there. So only by voice tapes do we know what happened. And of course, the place is still 1989 or something when that happened, and it's still a black hole in Ukraine. So that maybe Putin can have that part of Ukraine. I'm sure the Ukrainians are giving that part back. So I'm kind of setting the stage for why. Look at the phase curve. You know, it's kind of got weird angles, but look at the bump it's got on it. The more unstable your system is, the narrower that mountain becomes. You see what I'm saying? So in other words, if that pole moved out farther and farther to the right, this system would compress like this, and my stability would be almost a spike. So I have to raise the gain up here to put somewhere near this peak region, covers a bandwidth of almost from 10 to 2. So I have to put my gain such that this is going to be my crossover frequency. That's the problem. That's what makes control of unstable systems so difficult, because your gain variation has to be fairly exact and predictable, right? And I didn't put that inner loop pole on the real axis. It started up here, and it's moving out, and there's no way I can stop it from moving out. Look at the damping's 0.14 at the required overloop bandwidth. And the system is very oscillatory. It's going to have a steady state value of 1 eventually, right? Or close to 1 eventually. It gives me this nasty oscillation. The inner loop rise time spec was not met. I can meet all the rest of the specs for the inner loop, but I can't meet the 10. The control system must be ultra reliable, so I'll lose the airplane if it disconnects. So I need like 4 inner loops, don't I? I need a quad redundant digital control system, which all airplanes have now. They're flying with digital fly-by-wire. They'll have quad redundant. They'll boot out the bad computer. So the reliability is crucial, and I have to realize that if I go away from my equilibrium condition, control may not be sufficient to bring me back. So I don't want more bandwidth than I have to have, because more bandwidth means the probability of this third thing happening is more probable to happen. The lower bandwidth, the less that's likely to happen. So with those 3 caveats, I go in, and this is my inner loop response if I put the roots on the real axis. So I don't quite get the rise time I wanted. I wanted a 1/10 of a second rise time. This should be a little steeper. The drone, especially, someone's going to say, well, the drone doesn't care. There's no pilot in it. The laws are still there. The mathematical laws are still there. And you're still going to lose the drone if you make it too unstable. So don't. So those are all arguments against stability and for a lower bandwidth if you can get it. All right, so then we'll go into the outer loop one more time with this 6/60. The end result for my size with 2. We'll show the size 2 in a second, but I wanted to show you, if I take my OLTF2 and put a gain of 50 in it, I get the blue line. The blue line is going to give me a bandwidth just about 10, around 8 or 9. And here's my closed loop. This is what I'm being paid for. The closed loop bandwidth's out here. So I'm very close to the bandwidth spec. I'm going to try to sell the customer on this. It's a little lower bandwidth system, which I like, knowing the pitfalls of unstable control. A little bit slower system, and it meets the steady state requirements. It's got 60 degrees of phase margin. It's got a bandwidth close to 10. What I'm telling you today, the modern tools that you learn in control theory class hide this fact, right? Look what I can do in Simulink. Look what I can build. Look what I can do. And then you put it out there, and you're blacking pilots out, and you're crashing airplanes, right? And the systems are getting lost, and you don't know, and then you go back and figure out, oh, I violated Newton's law, which is Bode. Bode is Newton in control, right? You can't violate Bode's laws for control, no matter what new technique you learn in graduate class. You have to meet these fundamental requirements. The sensitivity function, 1 over 1 plus GH. If you integrate that with omega, right, that has to come out to be equal to, well, it depends if it's the log or not, either 0 or 1. Right, so if it's the log of this, it's 0. So if it's 0 or 1, if you integrate this thing over omega, if you have low sensitivity in some part of your curve, and you want low sensitivity because that means that the output doesn't change when you change your plant, then you're going to have high sensitivity somewhere else. And if your sensitivity is too high, you want this sensitivity to be low throughout the usable frequencies, and then the increase of it to occur by the Bode integral out at high frequencies, and you want it to flatten itself out so it doesn't peak at all. So we can actually look at the sensitivity of this.
Now I will run the unstable aircraft M file showing you the time response for the inner loop, the outer loop, the Bode plots, closed loop Bode plot, and the sensitivity function as the last plot.